Okay, very good. Welcome everyone to the Fields number 30 seminar. I'm delighted to introduce Payman Eskandari from University of Toronto. He'll speak about Ceresa cycles of Fermat curves and Hodge theory.
Yes, Hodge theory of fundamental curves.
Right.
So let me share my screen. Okay. Okay, hi everyone. Can everyone see my screen now?
Yes.
Okay, perfect. Thanks the organizers for the opportunity to speak here. So today I'm going to be speaking about Ceresa cycles of Fermat curves and Hodge theory of the fundamental group. So recall that on a projective variety, on a smooth projective variety, there are different notions of equivalence on algebraic cycles. So remember, an algebraic cycle is a formal Z linear combination of the set of closed, irreducible closed subschemes of the variety. And so we're actually going to, often in this talk, well, actually for most of the talk, we're going to look at algebraic cycles with coefficients in Q. So we're going to look at Q linear combinations of these. But there are different notions of equivalence on these things. And among these are rational, algebraic, and homological equivalence. So rough definitions, rationally trivial cycles are, these are, the subgroup of rational trivial cycles is generated by differences of cycles that can be deformed to one another along P1. Algebraic equivalence would be along an algebraic curve. And then homologically trivial cycles are those that are in the kernel of the class map. So remember, recall that there's a class map going from algebraic cycles to cohomology. So co-dimension P algebraic cycles to H upper 2P, and the kernel of those things are homologically trivial algebraic cycles. So these homologically trivial ones would be the boundaries of topological chains, so topological singular chain. So here we're looking at the variety as an analytical space, and topology is the analytic topology. Now, so throughout this talk, I'm going to be using this notation by script ZNXQ. I would mean the space of algebraic n cycles, so dimension n on x with coefficients in Q. I will be using superscripts RAT, ALG, G, and HOM for rationally, algebraically, and homologically trivial subspaces. And then so one has these inclusions. So a rationally trivial cycle is algebraically trivial, and algebraically trivial cycle is homologically trivial, but these inclusions are in general strict, and we're going to say a little more about that now. So, for zero cycles, algebraic and homological trivial are the same. For divisors, so these are co-dimension 1 cycles, there's a theorem of Matsusaka that says that after tensoring with Q, these things will be the same. So actually, so this will be 0 if you work with divisors. So if you're trying to find an example where homological and algebraical trivial cycles really are, those notions are really different, you have to go to look at varieties that at least have dimension 3, and there's a theorem of Griffiths in 1969. It says that if you take a general quantic in P4, then the rational Griffiths group is non-zero. So in other words, there's an algebra, there are homologically trivial cycles that are of infinite order modulo algebraic equivalence. And then Clemens in 1983 has shown that actually this thing is not even finally generated, even though it's counted. So, now let X be a curve, and so this notation is actually, it's going to be sort of stay in the talk, so it's important to try to remember this. So if X is a curve, by Jack you mean the Jacobian of X, and then if you take a point E in X, by X sub E, it would mean the image of X under the embedding of X into its Jacobian using the base point E. So you send a point X to X minus E, and that's going to give you an embedding of X into the Jacobian. So the genus has to be bigger than or equal to 1 there. And then xe minus, by that we mean the image of xe under the inversion map, so multiplication by -1 on the Jacobian. And it's easy to see that this difference is homologically trivial. It's homologically trivial one cycle on the Jacobian. And a theorem of Ceresa asserts that if you take a generic curve of genus at least 3, by the way, again, so, if you're trying to say that this is not a, you want to distinguish between homological algebraic triviality. So again, by that first observation that you want to go to dimension at least 3. So you want to at least, look at something that has genus 3 here for the curve. And Ceresa proves that for a generic curve of genus at least 3, that cycle is not algebraically trivial. And then so by this difference, so this difference we're going to refer to it the Ceresa cycle of X with base point E in this talk. There are also higher Ceresa cycles, but I'm only going to be discussing this one. Now, one thing to keep in mind is that this is for a generic curve. But up until this point, there weren't any explicit examples that would distinguish between homological and algebraic equivalence. The first explicit example of a homologically trivial cycle, which is not algebraically trivial, was given by Bruno Harris in 1983. So he showed that the Ceresa cycle of the Fermat curve of degree 4 is not homologically trivial. And the way this was done was as follows. This is gonna, these ideas are gonna appear later on in this talk too. So he showed that he was able to express the Abel-Jacobi image of the Ceresa cycle in terms of iterated integrals. And then for Fermat curves, these things become really, really nice. And then by using that, exploiting that, he was able to show that for a Fermat curve of degree 4, the Ceresa cycle is not algebraically trivial. Shortly after, Harris-Bloch, by using an elliptic argument, was able to show that the Ceresa cycle of F4, Fermat degree of degree 4, is in fact of infinite order modulo algebraic equivalence. Now, more recently, so these results are all in the 2010s. Otsubo and Tadokoro have been able to generalize Harris's method. So, and they've obtained non-triviality results modulo algebraic equivalence for Ceresa cycles of some other examples. So the point is that they really build on Harris's idea. So you find sufficient conditions for non-triviality of the Ceresa cycle modulo algebraic equivalence in terms of non-integrality of some integrals. And then those integrals, in the case you're dealing with the Fermat curve or quotients of it, so on and so forth, those integrals, there are special values of very nice functions, like hypergeometric functions, actually. And so, so basically, you have a sufficient condition to prove this type of result, non-triviality modulo algebraic equivalence, if you could show that those integrals are not integers. And then you can do that numerically when you're dealing with specific examples, and that's exactly what they did. That's what Harris does, and that's what Tadokoro and Otsubo do in these examples. And that's why, it's like Fermat curves of degree up to 1,000. So this sort of argument, we're going to come back to this. In the last slide, I'm going to say more about this technique. But you're always limited by, you have to, in the end, always there's a numerical calculation. But now the purpose of this talk is to prove the following theorem, which is a joint work with Kumar Murty, that the Ceresa cycles of Fermat curves of prime degree greater than 7 are of infinite order modulo rational equivalence. So it's not algebraic, it's rational, it's weaker than that, but at least you're getting an infinite family, and you're saying they actually have infinite order, not just non-triviality. And the proof combines several results on Hodge theory. So basically, several transcendental algebraic geometry results, Hodge theory of quadratic integrals on the curve. And then on the other hand, 2 results of Gross and Rohrlich, which are more number theoretic. It combines these results. So the goal would be to basically go over this proof. Any questions up to this point? Okay. So the plan for the rest of the talk is the following. I'm going to start by a brief review of the definition of the Abel-Jacobi map. And then we're going to talk a little bit about X groups in the category of mixed Hodge structures. And by the way, so for essentially all of this talk, every time I talk about Hodge structures, these are all rational. We're forgetting the integral structure. And then we're going to talk a little bit about Hodge theory of fundamental groups, and then we're going to go over the proof, and then there's going to be some final remarks. So as I said, so our result is about algebra, about rational equivalence, and I'm going to make some final remarks on algebraic equivalence. There's also algebraic equivalence, and there we're going to actually go back to the results of Harris and the argument of Harris, basically, take another look at that. Now, some of these things, the first two items were also in the pre-talk slides in much more detail, but I just want to go over them very briefly here. So some sort of a shorter version of this, what we had in the pre-talk. So let's start with the brief review of Abel-Jacobi maps. So first, notation, some notation. Suppose you have a Hodge structure of odd weight, 2n-1. Then the intermediate Jacobian of that is defined to be this quotient. So you take this is the underlying complex vector space, and you mod that out by Fn. So remember, the weight is 2n-1, and you're modding out by Fn of that, and then plus the underlying rational vector space. Now, for a second, suppose H was an integral Hodge structure, actually. Then you're talking when you take the intermediate Jacobian, you instead of modding out by HQ, you can mod out by HZ, the integral lattice. And then what you're going to get in that case is that because you took exactly the middle ones, here I put n where the weight is 2n-1, what you're going to get, so if you had the underlying abelian group here, you would actually get a compact complex torus. So, in the case that you're working with H1 of a curve, for example, this would be exactly the classical Jacobian, basically, of the curve. Again, if you're taking HZ here. And then modding out by HQ would be like taking that compact complex torus and actually modding it out by its torsion subgroup. One thing that I want to say about that compact complex torus is that in general, so even if you're dealing with a cohomology of a smooth projective variety, still in general, this compact complex torus that you're going to get is not going to be an abelian variety. It's not going to be it's not going to be algebraic. So, for basically the lowest degree and highest degree, it is going to be, you're going to get Albanese and Picard varieties, and then everything in the middle, all weights in the middle, you're probably not going to get anything algebraic. So by JH, we mean this quotient here. And now the Griffiths Abel-Jacobi map, and everything here up until the very, very last slide is tensored with Q. So the Griffiths Abel-Jacobi map tensored with Q is a map, which can call it denoted by AJ. So it's going to go with from homologically trivial cycles modulo rationally trivial cycles. So this is the homologically trivial subgroup of the Chow group of n cycles. Goes from there to this intermediate Jacobian, and it's defined as follows. So first thing to note is that this guy here, so this intermediate Jacobian, actually it can be identified with this quotient here, and the point is that see, H lower to n+1 has weight -2n-1. So going back to the previous slide, where we define this intermediate Jacobian, you have to mod out by f-n of that. And f-n of that would be, thinking about homology as dual of cohomology would be those maps that vanish on fn+1. So this quotient is now, all the dual of cohomology, functionals on cohomology, modded out by those that vanish of n+1, and then plus this Q lattice. So that becomes now functionals on Fn plus 1 of H2n plus 1. So the dual of that modded out by rational homology. So just a little bit of abusive notation here. So we're taking here, by this I mean the image of this in this dual space, of course. So this intermediate Jacobian can be identified with this quotient, and now given a cycle, a homologically trivial n cycle Z, if you pick a rational topological 2n plus 1 cycle. So that it has complex dimension n, so real dimension 2n. So that's why you have here 2n plus 1 cycle gamma, whose boundary Z. And then given a smooth, so given an element of this space, so you can represent it by something, by a closed 2n plus 1, smooth closed 2n plus 1 form omega, which is in Fn plus 1. So it's got at least n plus 1 dzis. And then you said, let's make this definition, the integral over gamma of the cohomology class of omega is defined to be just the integral of omega over gamma. So now, because you took a representative in Fn plus 1, one can easily see that this is actually well defined. It doesn't depend on the choice of omega. It's actually a well-defined element of this dual space. And then, but of course, there's a dependence on gamma, and to get rid of that dependence on gamma, you have to mod out by rational homology. So the Abel-Jacobi of Z, by definition, is the class of that functional integration over gamma in this quotient, which is now well defined because you modded out by homology, and that is just this intermediate Jacobian. That was the Abel-Jacobi map. And now a word about extensions of mixed Hodge structures. Now, okay, so given a mixed Hodge structure A, which, for simplicity, we're going to assume that it has a positive weight, 2n plus 1. And there's a theorem of Carlson, which is much more general than this, but in this case, it's going to tell us that there's a functorial isomorphism between extensions. So these X groups, all X groups that appear in the top are extensions in the category of rational Hodge structures. Extensions of A by Q minus N. This is canonically isomorphic to this intermediate Jacobian of A dual. And the isomorphism is as follows. So take an extension like this, and then you're going to send this to the following element of the intermediate Jacobian. You're going to pick a section of this map pi defined over C, which is compatible with the Hodge filtration. So let's call such a thing S. And then you also are going to choose a retraction of the map iota, which is defined over Q. Let R be such a retraction, and then you look at ROS, and now that's going to be a map from a C to C, so an amount of a dual complex, underlying complex vector space of a dual, and you're going to send the extension to the class of ROS. That's Carlson's isomorphism. As I said, it's more general than this. The condition and the weight being positive, you can get rid of that. It's a general result about extensions of mixed Hodge. Now, if you take A to be H2n plus 1 of X, X being a smooth projective variety, then what we get is that we can identify the extensions of H2n plus 1 by Q minus N with the intermediate Jacobian of of homology of 2n plus 1 degree homology. So the reason this is important and interesting, it shows up here, is that we're gonna the Abel-Jacobi map takes algebraic cycles to an intermediate Jacobian like this, and then but this can be identified and extended with X group of mixed Hodge structures, and then so you get from algebraic cycles to X groups of mixed Hodge structures. Okay. Any questions up to this point? Okay. So now let's spend a couple of slides on Hodge theory of pi1. So I didn't put anything in the pre-talk on this. Let's go over this a little more carefully. So let X be a smooth, but not necessarily projective complex variety. And so it's important to keep in mind here for this, this picture here, you're not assuming that your variety, your complex variety is actually projective. And let's take E to be a point in X. This E is going to be our base point, and then you're going to consider the map from this group algebra, the fundamental group. So fundamental group here is the topological fundamental group. We're thinking of X as, as a complex manifold, and this is the classical fundamental group. From this algebra, group algebra to Q, which sends every element of pi1 to 1. The kernel of that is called I, and then by some old works of very nice works of Chen, KT Chen, one knows that the elements of this quotient of this guy. So these are functionals on I that vanish on n+1 power of I. These functionals can be described using a homotopy invariant. So closed means homotopy invariant. Using homotopy invariant iterated integrals. So iterated integrals, these are integrals over simplices, and closed means that the value that they produce is not going to depend on the homotopy class of the loop. But the point is that the elements here can be written as some iterated integrals, and then Hayne has used this description to define a mixed Hodge structure on this space. So we're going to denote this mixed Hodge structures by Ln. So the L I'm using because it's like length, because these are iterated integrals of length at most n. That sort of explains the notation we're using here. Now, this mixed Hodge structure, so I'm going to take it basically as a black box here. The only things I want to mention about is that it's functorial with respect to the pointed variety. And also these inclusions that you have, these are morphisms. So really you're getting end objects in the category of mixed Hodge structure. And then H, see, as I said, so these are iterated integrals. So, just sort of to give us some sort of rough idea here, each of these things can be written as an integral, and then, there's differential forms that show up there. The filtrations weight and Hodge is defined sort of, in the way that you would expect, building on, how those filtrations can be described for cohomology, basically. So you look at, so first thing is that, one shows that all these iterated integrals will be obtained if we just restrict ourselves to working with differential forms that have at most logarithmic, smooth differential forms that have at most logarithmic singularity at infinity. And then the weight filtration is defined in terms of the order of the poles, basically, and the Hodge filtration is defined in terms of how many holomorphic differentials you're using. And now one thing that I want to mention is that L1, so this length 1 this is just H1, H upper 1, and this is independent of E. But then if you look at higher length, what happens in higher lengths, these mixed Hodge structures actually do depend on the base point. So now, in this talk, we're particularly, we're only interested in the case that n is 2, so quadratic iterated integrals. And then so these are, these are functionals on the augmentation ideal that vanishes on I cubed. Now, one has a morphism from L2 of xe to H1 of x tensor H1 of x. So how is this morphism defined? So, take an element of L2, so that's class of some f being a function on I, which vanishes on I cube. And then the element that you're going to correspond to that here is as follows. So H1 tensor H1 upper 1 is the dual of H lower 1 tensor H lower 1. And so given an element of H lower 1 tensor H lower 1, so class of gamma 1, class of gamma 2, gamma 1, gamma 2 being elements of the fundamental group of X with base point E, you're going to send this to, so gamma 1 minus 1, gamma 2 minus 1. So these guys, this is in I and this is in I. This whole thing is going to be in I squared. And then you evaluate F on that element. And now this is actually going to be well defined. So if I change, if I take a different representative, it's going to be well defined because this F vanishes on IQ. And now the kernel of this map, so what's the kernel of this map? The kernel of this map, so as we can see from the definition, would be those F, classes of those Fs, which vanish on I squared. I'm going to get I squared here. Which vanish on I squared, so the kernel is just well, those that vanish on I squared, that's just H1, H upper 1. It's L lower 1. It's those that have length 1, so it's first cohomology. Any question about these two slides, maybe? Okay. So now we're gonna go back. So from this point on, we're gonna go really about talking about the case that we're interested in. So from this point on, X is gonna be a smooth projective curve over C, and we're gonna take two distinct points, E and infinity, in X. And we're going to identify cohomology of X, first cohomology of X with first cohomology of the punctured curve X minus infinity through the inclusion of the open curve into the compact curve. And then we're just going to abbreviate that. I'm just going to write H1 for that to simplify the notation a little bit. And then by the previous slide, see in the previous slide, we had these maps going from I think there was something here in this, oh yeah, so there's also this thing in, right, there's also, yeah, so there's something here that I forgot to mention, a good thing that I did put in the slides. So the kernel is H1, but what's the image of this map? The image of this map, one can show that it's the kernel of the Cobb product. So the Cobb product going from H upper 1 to H upper 1, H upper 1 to H upper 2. And the kernel of that, let's denote it by H1, tensor H1, the whole thing prime. And the image of this map is the kernel of the Cobb product. Now, right, so by what we just said, going back to the case of interest with X is a smooth projective curve, and these two distinct points are taken. So L2 of X, so maps into, okay, so now, for the punctured curve, the kernel of the Cobb product is all of H1 tensor H1 because H upper 2 is 0. So the bottom row here is here the image of, so this map is the map of the previous slide. Sorry, this map is the map of the previous slide. Now it's going to be surjective because Cobb product vanishes on that, and that's the kernel. So you get this sequence for the open curve, and for the compact curve, you get this sequence here, and that's the kernel of the Cobb product. Now, so we get these two extensions that are going to play a crucial role in the rest of the talk. So let's give these two extensions names. I'm going to refer to the extension, the top extension by E sub E, and then the bottom extension by E sub E infinity. So, so this is an extension that you're getting from quadratic iterated integrals on a punctured curve X minus infinity, taking E as the base point, and this is the extension that you're just getting on the compact curve with E as the base point. So you get these two extensions, and okay, so EE it's an extension of a kernel of the Cobb product by H1, and we're going to use Poincare duality to bring this H1 to the side. So identify this with the extensions of a H1 tensor kind of Cobb product by Q minus 1. And then similarly, again, this guy being an extension of H1 tensor H1 by H1, and you're going to use Cobb product to bring H1 to the other side, and you get the extension of the third tensor power of H1 by Q minus 1. Okay, so now we're ready to go and talk about the proof of the theorem. So the proof is an application of the combination of the following results. So as I said, there are several results on the Hodge theory side, transcendental algebraic theoretic results, and then there's a couple of number theoretic results that appear here. So the the Hodge theoretic results are these two. Well, so works of Harris, these two items. So Bruno, Harris, and Pulte on the relation between Ceresa cycle and the extension EE. We're going to talk about this in detail in a bit, in a few minutes. So these are results from the 80s. There are works of Kaenders and Darmon-Rotger-Sols, much more recent, 2001 and 2012. These are the extension corresponding to the punctured curve. So the extension corresponding to the punctured curve includes more information than the extension corresponding to the compact curve. The one for compact sort of sits inside the one for the punctured curve. And then, so these are the Hodge theoretic results. And then the number theoretic results are results of Gross and Rohrlich on points of infinite order on the Jacobian of Fermat curves. And then and then the other one is the well-known result of Rohrlich that says that on Fermat curves, if you take a point on the Jacobian of a Fermat curve, which is supported on the cusps. So cusps meaning the points where one of the one of the coordinates is 0. If you take a point on the Jacobian, which is supported on the set of cusps, then this point is a torsion point of the Jacobian. So now, remember what we're trying to prove. We're trying to prove that the Ceresa cycle of Fermat curves of prime degree p greater than 7 is of infinite order modulo rational equivalence, but well, because we're working with, the Abel-Jacobi map is tensored with Q, so that amounts to, so it's enough if you show that the Abel-Jacobi image of it, remember, this is the rational Abel-Jacobi image, is actually non-zero. So now let's start the proof. So the way I've sort of organized this argument is that, anytime we need one of these results, anytime we need one of these results, I'm gonna remind us of that result first. And then I'm going to use it to get what we want. So the first thing to recall is the theorem of Darmon-Rotger-Sols. So here's the theorem. So let's take X. So X is a smooth projective curve over C. And E and infinity are distinct points here, as usual. So let Z be a one cycle on X cross X. And then delta be the diagonal of X. Now, intersecting Z with the so Z1, 2, by that I mean the intersection of Z with the diagonal, but we want to think of that as something being in, so that's going to be a zero cycle. A zero cycle, it's on the diagonal, and we're going to think of that as an element of a zero cycle on X itself by identifying X with the diagonal. So that's a zero cycle on X, and then so by PZ, we mean Z1, 2 minus its degree times E. So that's now a point on the Jacobian. Now, this point is related to this extension as follows. So let's CZ be the H1 tensor H1 Kuhneth component of the class of Z. Now, if you go from right, so tensoring with CZ is a Hodge class. So tensoring with that is going to give us a map from H1, twisted H1 to H1 tensor Q. And then so pulling back along that is going to give us a map, which I'm going to denote by CZ inverse, going from extensions of H1 tensor Q by Q minus 1 to extensions of, H1 minus 1 by Q minus 1, but then, tensor everything with Q1 to make it extensions of H1 by Q0. And now this guy here is by Carlson's theorem. It's the intermediate Jacobian of H lower 1, or the, the dual of H upper 1. And then, but the classical Abel-Jacobi map, this is this is isomorphic to the points on the Jacobian tensored with Q. So homologically, right? So this is divisors modulo principal divisors, and then you tensor that with Q. Everything, because this was tensored by Q. That's why they're also tensored by Q. So you get a map from here to here, which we're going to call it CZ inverse. And then the theorem of Darmon-Rotger-Sols asserts that if you take, so in here, you have this extension E infinity. There's too many E's here, which is hard to say. I should have thought of that. But every time I speak about these things, I think that I should change the notation, but then I end up writing the same thing. But so this extension is an element here. And the image of that is now an element of the of this Chow group, tensored with Q, rational Chow group, subgroup of the Chow group. And so what the theorem asserts is that this point is just the integral of CZ over the diagonal times infinity minus E. So that's now a point on the Jacobian, and then minus PZ. So that's how PZ is related to this extension here. Now, let's use this result and try to prove that when X is Fermat curve of degree prime P greater than 7, and E infinity and E, this should be E, my apologies, infinity and E are cusps, then this extension is non-zero as an extension of rational mixed Hodge structure. So this infinity and E, we're taking them to be cusps here. And now, okay, so what you're going to take as Z is the graph of the automorphism of FP, which this automorphism. And this automorphism, it has two fixed points. Now, a little calculation will show that it has two fixed points. The fixed points are these two, where eta is a primitive sixth root of unity. So PZ, remember what PZ was. PZ was Z12. So when you intersect with this delta, you're exactly picking up the fixed points and then minus degree times E. So PZ is just Q plus Q bar minus 2E. So this is the point that we get. And then there's this theorem of Gross and Rohrlich from the 70s that says that if P is a prime greater than 7, this point is a point of infinite order on the Jacobian of FP. And now, on the other hand, okay, so Rohrlich tells us that infinity minus E is torsion on the Jacobian because these two are, because infinity and E are taken to be cusps. So going back to the formula of Darmon-Rotger-Sols, so this guy is because things are tensor with Q here. So this is now 0. And then this one here is something non-zero. So this is non-zero, and then so our extension is non-zero. So that's so far what we've proved by combining Darmon-Rotger-Sols and Gross-Rohrlich is that if you take Fermat curve of degree prime greater than 7, if infinity and E are cusps, then this extension is non-zero. So now the next step is to use some results of Harris and Pulte and Kaenders. So now we're going to be using results. Yeah. So again, these are Hodge theoretic results. So now let's recall these two results. I'm going to go back to the generality of just a small projective curve, and then we're going to apply to Fermat curve in a couple of slides. But in the more general scenario. Again, let's, right, so C delta is the same as before. And then we have the decomposition of rational Hodge structures. So H1 tensor H1 decomposes as the kernel of the Cobb product plus Q times C delta, that one-dimensional Hodge structure. So this triple product decomposes like this. And now remember our extension, E infinity, instead of calling it E infinity, if you don't mind, I'm just going to call it E infinity for now. So our extension E infinity is an extension of this guy by Q minus 1. So now you know you can restrict that to these two summands. And these results are going to describe those two restrictions to us. So the first is the theorem of Harris-Pulte. This is from the 80s. It says that the restriction of E infinity to this component, well, that is simply just, you know, the extension E from earlier. This is the extension that of quadratic integrals coming from the projective curve. Now, this is half of the image of the Ceresa cycle based at E under this composition. So this is now what you're doing is that you're first taking taking the Abel-Jacobi map. Abel-Jacobi on the Jacobian variety is going to take us from a homologically trivial one cycles on the Jacobian to this intermediate Jacobian of H lower 3 of the Jacobian. But now, okay, so you can identify cohomology of the Jacobian with the exterior algebra on the cohomology of the curve, the compact curve cell. And so now this guy is the intermediate Jacobian of the dual of the third exterior power of H1. And so now, so this guy here, there's a natural injection from this intermediate Jacobian into this intermediate Jacobian. Now, how does this work? See, it's easy. A small little calculation would show that the map that goes from, so you've got the natural, quotient map going from this tensor product to which the third exterior power of H1. And one easily can see that that's actually surjective. So dualizing that, you're going to get an injection of this, and then you're taking intermediate Jacobians, you're going to get an injection of this intermediate Jacobian into this intermediate Jacobian. And now by Carlson, this intermediate Jacobian can be identified with this X group. And what Harris and Pulte say is that, so EE, which is here, is half Abel-Jacobi of the Ceresa cycle based at. So that's the restriction to this component, and then the restriction to this component, that's the result of Kaenders from 2001, which says that the restriction of E infinity. So now this component. Okay, so with the restriction to this component, so that's now going to be a point in extensions of H1 tensors C delta by Q minus 1, which can be identified with just a, so this is like H1 twisted by minus 1, so it can be identified with this. And so it can be, so Carlson and then Abel-Jacobi map. You can identify it with this guy here. So there should be a subscript Q here. Tensor with Q there. So as a point, the restriction to this component as a point in here is this point. G being the genus and K being the canonical divisor of the curve. Okay, now we're going to apply these two results to our setting. Again, X is the Fermat curve of degree P, prime P, and infinity and E, we're going to take them to be cusps again. So now we know that, okay, so P being greater than 7, we now know that this extension is non-zero. But then, okay, so looking at these, the restriction of that extension to this component and to this component, the restriction to this component by the result of Kaenders is sorry, my apologies. So yeah, so E infinity is 0. So we're going to look at its restrictions to this component and this component. The restriction to this component is 0 by the result of Kaenders combined with Rohrlich, actually, right? Because so Kaenders would say that that restriction is this, but this is going to be supported on the cusp. We took infinity and E to be cusps, and then so that component is 0, and well, the whole thing being non-zero, the whole extension being non-zero, shows that the restriction to this side is to this component is non-zero, and then by the result of Harris and Pulte, we get that the Abel-Jacobi of the Ceresa cycle has to be non-zero. So that is what we do. So up until this point, what we've shown, well, we've shown our result, except that the base point is not arbitrary. So up until this point, this E has been a cusp. But now, okay, so we want to get rid of that hypothesis and prove the result get the result for arbitrary base point. Now, for arbitrary, so here's what does now. Again, you know, there's the theorem of Harris and theorem of Pulte that I'm going to use again. So again, I'm going to go to the general picture here. Now, arbitrary curve. Now, the third exterior power of H1. So this is, you know, this is like the third cohomology of the Jacobian. It decomposes as the primitive part, primitive cohomology of the cohomology of Jacobian, and then plus this guy here, where this bar, what it's doing is that, remember this C delta was the class of delta in H1 tensor H1, and the bar is taking it to H2 of H1. So you get this decomposition in the category of rational Hodge structures, and then theorem of Harris tells us that the Abel-Jacobi. So the Abel-Jacobi is an Abel-Jacobi of the Ceresa cycle is an element of the intermediate Jacobian of this guy. So now you can restrict that to this component and this component. And what Harris shows, this is his ACTA paper actually, he shows that the restriction to the primitive cohomology is independent of the base point. And then for the restriction to this other component, that's a result of a Pulte that says that the restriction of this Abel-Jacobi of the Ceresa cycle to this component. Now, again, there's a similar identity as before. You know, you can identify what you get in the, you can describe the image as something in the Jacobian tensor with Q. There's a Q missing here, and it's going to be this point here. And now, okay, so again, you know, back to the case of interest for us, Fermat curve. But for now, so we're trying to get rid of the independence on the, you know, get rid of the so far we've shown that you know, Abel-Jacobi of the Ceresa cycle is non-zero if the base point is a cusp, and we're trying to get rid of that that hypothesis of E being a cusp. But for the moment, still assume that E is a cusp. So if E is a cusp, then this guy here being supported on the cusp, this is going to be a torsion point of the Jacobian. So, you know, tensor with Q, that just goes away. And then what we get is that, so, you know, here, you know, the image of the Abel-Jacobi here was non-zero. So it's a restriction to this portion is non-zero, right? But now, well, the restriction to this portion is actually independent of the base point by Harris. So now we get that actually, so that component is actually non-zero for any base point, and hence the Abel-Jacobi of the Ceresa cycle is non-zero for any base point actually. So I'm almost done basically, but because there is time, I'm going to also go over this slide that I promised. So here, see what we did here is that we talked about a rational equivalence, not algebraic equivalence. And now let's talk a little bit about algebraic equivalence here. So how would one, you know, get results about non-triviality with respect to algebraic equivalence, you know, using this line of thought? So here's sort of general observation. Let Y be a smooth projective variety and Z a homologic trivial n cycle. And now in this slide, I'm actually going to take the integral of the Jacobi map. So this is now, I'm modeling out by the integral homology now. Now this guy here, so that's the Abel-Jacobi image of Z. But now this is the main main and very simple observation, that if Z is actually algebraically trivial, then this guy here, this will vanish on Fn plus 2 of H2n plus 1. And the point basically is that if Z is algebraically trivial, then you know this boundary. So this is something whose boundary is Z. You could basically choose that so that it lies in a complex manifold of dimension n plus 1 now. And then Fn plus 2 there will just be 0. So that's why this Abel-Jacobi of Z is going to vanish on that subspace. And that's going to give us a sufficient condition for non-triviality modulo algebraic equivalence. And this is what Harris exploited in his original paper. So Harris expresses the Abel-Jacobi image of the Ceresa cycle in terms of, for any curve in terms of iterated integrals. So that basically, this identity that we looked at before. And then in the case of Fermat curve degree 4, using the idea that we just discussed, and then the fact that these integral becomes really nice, he obtains a sufficient condition for algebraic non-triviality in terms of a non-integrality of an iterated integral which involves holomorphic forms. Now, because you're trying to show that something is not an integer, some explicit integral is not an integer, now you can just do it numerically, approximate it. And that's what he does. Shows that it's not an integer, and hence he gets non-triviality modulo algebraic equivalence. Now, similar line of thought has been more explored by Otsubo and Tadokoro recently in the 2000s, more recently in the 2000s. And so again, they get results about Fermat curves and quotients of Fermat curves in the case of Tadokoro. But the last step of these arguments is always a numerical calculation. So you get a sufficient condition, which is like not a numerical thing, but to verify that, now you have to approximate it numerically. And that's what they do. And that's why you don't get results that, for like infinite families, things like that, they're not getting definitive results. Also, this line of thought here, wouldn't say, it's hard to get something about, non-torsionness, because now, very simply, sort of like, roughly speaking, now it's like trying to show that something is not a rational number, and you can't do that. We can't do that numerically, obviously. But now, what we've done here is that, we've used the result of Darmon-Rotger-Sols and then Gross Rohrlich. By using those, we've avoided numerical verifications. And in fact, we've been able to show that, Ceresa cycle has infinite order, but the cost is that we only get it modulo rational equivalence and not algebraic equivalence. And one very interesting question, which I'm gonna end my talk with this question, is whether one can somehow strengthen this and maybe somehow exploit this idea in some way to actually get a result regarding algebraic equivalence. Okay, so thank you, thanks everyone for listening.
Thank you, Payman. You can't hear everybody applauding, but I'm showing. Thank you that was a really clear talk. Do we have any questions from the audience? I think you sort of answered everybody's questions already. So the question still remains what we can do about the infinite order modulo algebraic equivalence, right?
Yeah, absolutely. Yeah.
This really seems to require some new idea. That would be very interesting. Okay, does anybody else have any other questions? You're all very silent today.
So one thing that I forgot to mention is that actually, so same thing actually gives, because the result of Gross and Rohrlich is actually about points on quotients of these Jacobians.
That's right.
So one get the same thing actually about quotients of
right. Okay, very good. So if I don't see any hands up or any questions in the chat, so I'm assuming that everybody is really happy with the presentation and is busy working on trying to prove the theorem for algebraic equivalence. So okay, thanks again to Payman.
Thank you.
Next week, our speaker is Clifton Cunningham from Calgary. He'll speak about automorphic forms on G2. Good. Okay, thank you. See everybody next week. Bye. Bye.
Bye-bye.
Thanks, Payman.
Yeah, thank you.